It's here now. So let's start the lecture today. So what we did yesterday was basically learn how to do presentations for proposals. And then, of course, we started to talk about all the ethics considerations for publications. And, of course, the next thing is also what's really important for you when you write your own publication. You need to understand how people read publications, and especially for you also, how to better read other people's publications. So basically, critical analysis of publications are really essential. The tendency is for students who enter a field, they assume if there's a big name on a paper, it must be fantastic. But it can be fantastic, but you have to critically analyze whether it really is. Yeah, so don't be blinded by names, by institutions. Some of the great progress comes from countries you don't expect it, or let's say they are not as famous. And so historically, when they report something, other people just don't believe it. Of course, yes, they do critical reading and assume just it can't be true. But that's the thing. If you really can do well critical reading and you see if that is true what these people report, then it's actually substantial advancement. Yeah? And so the next hours after this one, we'll do some paper analysis. Of course, the next week is your presentation, but after this we do then critical paper analysis. And I selected some papers on electrospinning, but we'll also do others. And in order to make a thorough job of analyzing these papers, of course, you should know a little bit about electrospinning. And I'm not sure whether everyone is familiar. So I'm going to explain a little bit more how you can synthesize nanomaterials with this electrohydrodynamic method. And yeah, overall, this is basically electrospinning. Some of the labs here have actually devices to electrospin. It's Dr. Pike's lab, Dr. Lee's lab, and so on. They definitely have this equipment here. And of course, when you go around Korea, you also find other labs like in KAIST and KIST who also have this equipment available. So why do now recently a lot of people publish in this field? The key thing is, of course, that this allows now to make nanoparticles or nanofibers. And nanomaterials is the big advancement in the sciences, in, let's say, in naming for the past about 10 years or 12 years. Before that, it was always called colloid science, but now we call it nanotechnology, and then suddenly you need nanomaterials. So all colloidal particles, all colloidal systems that we had before are now summarized basically under the term nanomaterials. And this electrodynamic or electrohydrodynamic phenomena allow actually to make a lot of variety of materials into the nanos. That's why we look into this. And that's why a lot of papers are out there that we can then critically analyze. And the battery, oh no, it still works, but the battery might be dying of this device here. Okay, so yeah, these are just some examples. These are cover pages made by my group, but there are many more out there. So this is barium titanate nanofiber. So this is a 200 nanometer scale bar here. The crystalline, it's a perovskite, of course. And yeah, in this size range still, you have, of course, the tetragonal phase, which is highly active for capacitors. And here is a titania fiber. And of course, titania can be made very thinly. And yeah, it's interesting for a number of applications, filtration or photocatalysis, or battery materials nowadays for electrode materials, if you combine them with lithium ions and, of course, some other compounds. Why now recently also ceramic materials? That has not been done before. That is rather new in the scientific history. Typically before, people only made polymers. For about, we'll say, 150 years or so, they were looking into polymers mainly for electrospinning. And now for the last about 10 years or 12 years, people do also now ceramic materials. And of course, they also look into making metallic fibers, but also very recently only. Yeah, so just what was happening in history, and there are several things that occurred. Of course, electric phenomena are all around us, so you can observe a lot of things in nature. Another part is, people, since we're dealing with energy, of course, energy is a lot of connected with electricity, and there are some people who discovered how you can store electricity. The oldest one is probably the Baghdad battery. After that, the recent one was Volta in Italy, who built basically the first battery. That's why we have volt as a unit for the power, or the potential of a current. And so people then use these batteries that were developed at the time, explored in several ways. And they also discovered, similarly, what the Greeks already knew, that when you rub certain compounds like amber, then you get actually a lot of charge developed. So not a high current, but a lot of charge. Sorry, a lot of voltage, but not a high current, so not a lot of charge. And this can be also achieved then through other devices, like here this Van de Graaff tribocharging system. And then, when you rub something, you get basically the charge on the chain, which is insulated here. And then whatever you connect it with, it does something. Just since I talk about tribocharging, do you know the Greek word for the word amber, where the people discovered that you can charge when you rub something? You should be very familiar with this. It's a standard word you use all the times. Yes, yeah, definitely. Any guess? What would be, if you have something, you rub it, it shows electricity. So obviously, what would you call that material? Okay, the Greek word for amber is electron. So that's why we call things nowadays little negative charges electrons. Yeah? Because when they rubbed it, they found the electricity, and yeah. So these are things connected. So it's very direct. You rub something, ooh, electron. It's electron, and this has an electricity. Okay, so here, of course, they didn't rub amber. Tribocharging can be done through a lot of processes. And with this high voltage, of course, you see then you get specific phenomena. And here the water droplets don't drop just down from a bucket, or here they start to actually spray in a cone. And so they break up into smaller droplets, and due to the charges, they separate and spray. Similarly, when you hold something into your hand, that's the same thing. You have to be insulated. If you're not, it's not going to work, of course. Then you just make a current through your body, or over your skin, not through your body, over the skin, and nothing happens. So what's in this section here of the picture, since we're talking about critical analysis, tribocharging, what is expected for such a person if it has a high potential on the body? What do you expect? The hair should stand out, yeah. So why do you think it's not happening with this person? It's a wig, yeah, so tied down. So if there's anything standing up, it has to. There's some small things, but it will be so tiny that you can't see it. Of course, this is not a photograph. It's a rendering of something, so you won't see that. But if you were to do this nowadays, of course, you would probably pick someone with really long hair and then standing up. Okay, so and this is published in 1746. It's a French book, Essai sur l'électricité des corps, and this is one of the things people played with there in the weekends. But the first person to do a little bit more quantitative study was actually William Gilbert. And William Gilbert, he actually was for Queen Elizabeth I. He was the chief physician, and he also did a lot of experiments. The main focus at this time was magnets. So he played a lot with magnets, but of course magnetism and electrical fields are somewhat connected, as you know. You can easily create a current by using magnets that are rotating with conductors set around. And so he also played a little bit with electricity. And what he did is basically to take a liquid surface, expose it to a static, a strong electric field, and then he saw that the liquid started to form bumps. So, and he's the first one to report it in his book, and that's his book. It was published, here, the year is given, they only mentioned it shortly, but he's the first one to describe these cones. Nowadays, we call of these cones Taylor cones that are happening. And just want to show you shortly what happens when you have a liquid. So you have a liquid surface. You oppose on the other side now a metal plate, or typically actually easier if you just take amber again or some piece of glass that you rub with something. And this then is highly charged. This should be, of course, then positively charged here because electrons are taken away. And then down here, of course, you have an electric field. And now the liquid starts to deform, and you start to form little bumps on the surface. And these bumps depend, the shape and height and so on depends on the viscosity of the liquid, but it also, the density depends on the electric field strength. And then you form typically several of these next to each other. Yeah? And of course, we don't typically work now just with liquids like this. You can do this too if you want to electrospin large quantities, but in the lab you want to have more control, and also for certain synthesis procedures on a large scale you want to have more control. So what you do, you can I wipe this out? I think it's not important for us or for anyone. Dates or something, okay. If you have then basically a needle, and this needle is typically a diameter of around 1 to 2 millimeter. And then you squeeze out a droplet of a liquid. Yeah? And of course, this is the bottom of this, of the needle. And so far, the typical behavior, the droplet gets a spherical shape. Why do we get a spherical shape and not something else? What's the key force for this? Surface tension, yeah, surface tension. So now you have to apply something to deform this droplet to also get a cone. So that means you put on electrical forces. And that means with a little bit of charge, this system then looks a little bit more like this. And if it's more charge on the system, then you come to a nice cone. Yeah? And as you deform it, basically, and it's going to stretch more and more until you finally come to this cone here. And when you have such a cone, you actually will observe then that material is being emitted. Typically now here, this cone starts spraying. Or under certain conditions, then you can also start to electrospin, basically making fibers. So when you have the system, you can then achieve basically spinning conditions or spraying conditions. And we'll see how to make nanofibers out of this. So here's basically the setup. You have a syringe. The flow rate is really important, so you have a precise syringe pump. Because the amount of material that comes out here defines how much is being deposited here. If you push out a lot of material, obviously, it will still be influenced by the electric field, but it won't really follow all the physics laws to make it into very small, fine droplets, because the amount of charge that you can put in versus the amount of liquid then will not be in proper balance. So you have to control really low flow rates in the order of milliliters per hour. And then you have a certain distance here, anywhere from 2 centimeters to 30 centimeters. The reason why you have to limit it in further distances usually is the power supplies. because it's very difficult to buy very high power supplies, but you can find easily some in the range of 10 to 30 kilovolts. Much higher is not so easy to get by. And so that limits basically the distance for working, and because you need a certain electric field strength. So the electric field strength is the key, not so much the distance or the power, it's the electric field strength. And if you go a meter away, you need much higher power supplies. And then, yeah, you have a target. And the interesting thing is the target is just grounded. Actually, you don't have to ground it, because if you put in a potential on this here, anything around here has a lower potential. But that's, of course, the risk. If you don't ground this here, your material can deposit anywhere. It might deposit on your syringe pump. It might deposit on your power supply. So it's not guaranteed that you hit the target just because you call it target. Yeah, you have to put a lower potential on this system here, typically by grounding. Or another setup would be you take another power supply and put the opposite charge on this here. Now you definitely will move everything to this target here. There's still one other factor that could avoid that you hit the target. What else could that be? Humidity. Humidity, yeah, you could cause sparking. You could basically that you get breakdown of the whole system. But what else could be the reason that even though this is electric field strength is high, so from this train of thought you expect this material to definitely deposit here, even in this direction you have gravity helping. But what else could be there? And think about where these things are typically synthesized. Hmm? No, not contaminant. No. So these are nanomaterials. For safety issues, when you synthesize these materials, you have to work in an environment that is enclosed, and typically if humans want to be working on that, even though it's enclosed, you have a small gap, which means you pull in air. So you have a strong airflow, and the airflow through here can blow everything away. Yeah? So even though you have strong electric fields that guide the material to here, it's not guaranteed that you deposit everything here. When you look into the systems where people electrospin, airflow can actually blow everything to the side. So it depends how strong the airflow is. That's something, of course, then to control, that you put this in a section of the system, that you limit airflow, that you don't blow your material away. Okay, so just a few things. This is now what we use nowadays. Before, of course, people used the different systems. And let me just show you also, it's now 2012, so we are pretty advanced with understanding and with working on this. But historically, people observed these things already. So I showed you the one picture with electrospraying. Matthias Bose described this in 1745 also, that aerosols were formed by electrostatics. So this was definitely after Gilbert. Yeah, so Gilbert was earlier 16th century. Then we have Joseph Antoine Plateau. They also described breakup of water into droplets with electric fields. It was 1801 to 1883. That was his lifespan, so somewhere in that period. And then Rayleigh predicted the amount of charge needed to overcome surface tension, basically to form this here, or and to deform this thing. That was in 1882. He published this Philosophical Magazine. And then the Wiegand and Burton in 1912 published something on a fine liquid jet. So this is the first time now we're talking about fibers and not just droplets. And there might be, actually I haven't verified this yet, but there's a Sir Charles Vernon Boyce. He seemed to have made in 1887 the first nanoscale fibers derived from melt. So he published a paper in the Proceedings of the Physical Society, London, in 1887. And then other people, of course, followed after that. Interestingly, nanofilters, most nanofibers, and this in application for filters, most likely have been done in 1938 also. But typically at the time, always with polymers, not with ceramics. So a lot of things have been done over the time, and so nowadays we have actually quite some help with understanding from how these processes work, and that's one of the approaches here. Basically, people look into the balance of forces. So one thing was already we talked about, you have a spherical shape because of surface tension, and of course this is deformed if you have a droplet dripping down by gravity. It's pulling on it. Surface tension is of course pulling in to make it spherical. Then we have, when you have something ejected, of course viscosity is working against this, slowing this down. And then we have electrical contributions. And one is a normal electric stress. So by surface charge, of course, it wants to separate as much as possible. So it wants to break up the droplet, so pulling out. You get, because of the electric field, you get an electric stress that is in this direction. And then there's another electric stress, it's called electric polarization stress, is also pushing in this direction. That's basically pushing the fibers out, or the droplets out in this direction. So, and these are things that have been quantitatively described. We look pretty much just in one equation here now in this lecture. It's basically to understand how thick a fiber is here, especially towards then the end. The interesting thing is, of course, you see, you start with these electric fields, with really large diameters in the electric field. In the beginning, 2 millimeters, and of course it could be endless size because these cones form automatically then. And the liquid then thins down to about a micron down here, and then when it comes out, this fiber is being stretched. And how it's being stretched is actually going into a whipping mode. So these are just pictures from a high-speed camera. It's a little challenging to see for you probably, but you see what happens. So this is the so-called Taylor cone. You see this is a high viscosity liquid, so the electric forces do not overcome completely the shape. So you have still an impact on the shape that it's not a perfect cone, but it's you have ejection of material here. And then you see for the longest time, it's actually a nice thin fiber. It starts to get thinner as it goes down for the reason of evaporation, because you have solvents in there. And then at some point, suddenly you see there's a deviation, and then the system starts to deviate more and more. Unfortunately, the contrast is really challenging to see here. But you see, this is now this picture starts from around here. It's again linear, and then it starts to bend, and then now it's going over, bending more and more. And in the third one, it's very challenging to see, but it's also going left and right really much. Yeah? So that's okay. When you go to the labs and so on, you'll see how much whipping is actually happening there. And that is pretty much the key issue for this electrospinning. What happens here is, let me explain it just like this. You have your fiber coming down, and of course now you have a nice balance between the electric charges up here from the electric field on this fiber. So you have a straight push down, but of course you still have over the whole distance probabilities that the charges are not completely distributed evenly, and that means at some point you have the probability that it will deviate from its linear field a little bit, from a linear behavior, a linear motion a little bit, and once it starts to not be following exactly the field lines anymore, there will be a force correcting it, and the force will push it in the other direction. And then it's over here, then it will be pushed in the other direction. And what actually happens then, the fiber as it comes down will start to bend, and this bending then causes the fiber to move around in a spiral-like shape. So it's not a left-right whipping, it's a three-dimensional whipping, and you get then the fiber really fast moving out. You can do then force balances at different areas. You could say force balance, so basically a fiber that's down here moving in the electric field like this. You would of course have some electrical forces on it, and you have centripetal forces because it's in a circular motion. And from this you can start to establish about what thicknesses you can expect. But typically there are some other equations that are being used, and that is here. And that is now a system that is based just on the whipping interaction of an electrified jet in an electric field. And that was published by Friedrich et al. In 2003. So they found that you can actually predict the fiber diameter for a certain dimension and for certain systems by this equation. So the terminal fiber diameter, which means at the end when you deposit it on the surface, is related mainly to the flow rate, how much liquid you pump out, and divided by the current through the fiber. And you see these two parameters are squared, so they're really influential and important. But everything you see here is over a cube root, and this has, of course, to come something from that. You're dealing with a volume that you pump out, and you have to reduce the volume to a diameter. So obviously, you have to take a cube root to come from three-dimensional to one-dimensional system. And let's see what other parameters are in here. You have epsilon here. This epsilon is strangely not the liquid that you pump out. It's the medium that surrounds it, so it's air. So by influencing the medium, you don't have too much control over the system. Only the surface tension of the medium has some control. And yeah, the other parameters here, this is something that is assumed constant for this type of equation. If you work with a variety of polymers, this is true, rather true. So we have here, this is fixed as 100, so ln from 100 then. And this parameter is pretty much just the bending. So the fiber, when it bends like this, the curvature of this system here. So curvature of the fiber divided by the fiber diameter. And this is chi is around 100 for many systems. So that's why if you work with polymers, you only have really two parameters to play with. This one you can influence by adding salt or changing conductivity of your electrolyte, basically of your solution where your polymer is in. If you want to have highly pure polymers, of course, you can't do much about it. And this one here, yeah, that's this full control. Surface tension, you have some control depending on the polymer and the solvents you work with. Okay, so for ceramics, this doesn't work too well because this conductivity here is sometimes too high. Ceramics, you start out typically with ions in solution or with salt shale systems, but still there are ionic processes available in these systems, and these ions mean you get a high current through the fiber. And when that happens with a high current through the fiber, you get actually one other phenomenon. One thing is breakdown of the electric field, so electrospinning stops, and then electric field builds up again, electrospinning starts. So that is a big issue. But another thing is, if this current is really high, then suddenly also this parameter that has been simplified, as is stated here, is no longer true. So you have to go back and put in other parameters, recalculate, and then you get a better approximation that is also valid for a few more materials, especially for ceramics. But it's getting very complex. The equation has no analytical solution like this one here. It's only computational approaches are possible then. So you know a little bit now what people can do to play with the system. Interestingly, of course, as you see here, in this equation, one key parameter that I talked about all the time earlier is not listed at all. Which one is that? The rate of evaporation of the salt. Yeah, okay, that is also something that is not in there. So yes, if you the solvent evaporation rate will have an impact, but since this is the terminal jet diameter, and typically people measure this not in the wet state but in the dry state, that is an error in the whole experimental, systematic error in whole system as an experimental setup usually. And this can be controlled by just the amount of solvent to polymer, basically what's left over at the end. But it's a good observation, yeah. That's one thing that's typically not in this equation. What else is not in the equation? The height, yeah, the distance is not in there. That's a good point. So also there's a limit, basically. So these are things that have to be listed when you want to do that, but what else is not in there?
The diameter of that syringe goes up.
Yeah, but that is completely, it's almost independent. You can vary it quite widely. You can make it even narrower, because then if it's smaller, then it just a droplet gets larger where that is attached. So it doesn't matter. It can also be, you can use a sieve, it can be really, that's doesn't influence too much. There is some impact on this, but it's not too dramatic. But the one thing I was talking about always was electric field. Yeah, and where's electric field written into this equation? Nowhere. Yeah. So that's the interesting thing. The way they developed this equation, the electric field only appears basically through this parameter, either current through the fiber. Yeah. So that was very interesting to see. And of course, as I said, if this is not true, then suddenly the equation gets more complicated again. But the good thing is, with this equation, if you have a system that you can electrospin that falls within the range of such an equation, then you can actually tell whether you have a chance to move it towards nanofibers. Yeah? If you work with, if you have a certain flow rate and you make 10 micron thick fibers, and then you can plug it in this equation and see how slow the flow rate has to be to come to this value. And then if you see the flow rate has to be so small that my machine can't handle it, or that it's unlikely to be there, then yeah, you can easily predict that. That's the nice thing about such an equation. You can tell whether you have a chance actually getting there. Yeah? And also, you see, you can then manipulate, of course, all these parameters. Say, okay, I have to increase, you have to add some salt to the system. I have to pump really slowly. I'm going to add also surfactant to lower the surface tension. Yeah, this is pretty much the limits that you have. And then you can see in a simple calculation whether you have a chance to move towards 50 nanometer size fibers or not. There's, of course, another question then. After adding surfactants and salts, do you still get fibers, or do you basically end up with something that is mechanically not stable, so it breaks into small pieces or units? Yeah? Okay, so the next slide is about just electrospinning of a polymer. So this is polyacrylonitrile. So the nice thing about polyacrylonitrile, when you heat this, you can actually cross-link it through these groups here. And when you cross-link it on continuous heating in oxygen, so in air atmosphere, you then can form precursors that on continuous heating can turn into graphite. That's how graphite fibers are being made. So it's also an interesting material for energy, for combinations of graphite nanofibers combined with other materials for lithium-ion electrodes, and of course anywhere we want to have higher conductivity and a carbon source that is graphitic is of interest. And this polymer dissolves well, for example, in DMF, but there are other solvents you could use, and this here is DMF. So you see two methyl groups, here another carbon, and then the aldehyde here, and here an amino group. And when you electrospin, you just dissolve this, and here, so you see these fine fibers that you can form. A scale bar for this is 2 microns here. So you see they're not just a few nanometers. This is a 2 microns, so you're probably around 100 nanometers. Here it's actually 212 nanometers. So they're below 300 nanometers, which allows you to call them nano nowadays. And you see, of course, a big difference in dimensions compared to typical other fibers which are used as a support underneath. And yeah, here is now an entire fiber mat. So this is the support, and this is such a fiber mat. So these things can easily be formed. And when you want to do ceramic fibers, you have to do it a little differently. Now you need to use a polymer that does not leave anything over. So the polyacrylonitrile can be transformed either PAN fibers, polyacrylonitrile fiber, or on heat treatment to graphite. But if you don't want the polymer to stay over after heat treatment, use others. For example, polyvinyl pyrrolidone can be oxidized rather easily. You see there's no group here that can actually do cross-linking and making a graphitic structure. So that is actually a good thing. Another part is this polymer is available in very high molecular weights and does not respond strongly to ions. So when you add salts to the system, it stays dissolved, doesn't precipitate. And so that's a big advantage. Yeah, then we have titanium butoxide is the precursor. You have a variety. You can use titanium butoxide. You can use titanium isopropoxide. You can use pentoxide. There's a whole range of precursors out there. Why do you think people select certain compounds? What would be the difference? Yeah, of course, if you want to make a lot, maybe, yeah. And what's available just on a day in the lab. No, the precursors for salt shale is always same system. You're working with reactive ceramic compounds and organometallic compounds, actually. So you have basically here titanium. And now you connect groups around this titanium. And depending on how reactive you want it to be, you make it very accessible for chemicals. So basically you add small groups here, just like this. I'm not specifying it right now, just show you the space requirement. So you add a small group. This could be then, for example, CH3 only, or C2H5. Another possibility is you make these groups really bulky. Yeah? So you make the group like this, like this, like this. Of course, this is then three-dimensional. Yeah? So not just two-dimensional here as it's drawn. So now, if you want to attack here, either this or this, depending which chemicals you use, it's very hard to do an attack on these things, because when once you have these groups, you basically have little space to intrude and do a chemical reaction. Yeah? And that's the whole principle. Titanium butoxide is basically in between. Isopropoxide is more like this. And so depending what reactivity you want. If you want to have a high reactivity, use the shortest chains. The longer, they're less slower in reactivity. And then the bulky ones are even, so the three-dimensional systems, that isopropoxide will be C, CH3, 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 yeah? These groups are very bulky. This is the isopropoxide. Yeah, so that's the reason why we use a variety of these, but butoxide is a compound is okay. And then you need some compound that controls the reactivity. And you see there's no water in the system right now, just ethyl alcohol. So what we use is the water of the environment once you electrospin. And yeah, you use acid in it to control the pH for the chemical reaction. And of course, this acetic acid also does something in the reaction, but it doesn't cause the precipitation of the whole system. And yeah, then you electrospin, and you form then fibers, and yeah, then you heat treat them and let it furnace cool, and then you end up fibers. And here also you can make fibers in easily less than 200 nanometers. So we looked into characterization some time ago in the beginning of class. Do you remember how you can characterize fibers that are less than 200 nanometers? Let's see, if you make these fibers, how do you know you make something that is in the range of 200 nanometers? What equipment would you use to characterize? X-ray diffraction? I'm not sure. X-ray diffraction measures the crystallinity. It could tell you something if the particles, if there are crystals within and the size range of these crystals. That is a possibility, but we want to know the diameter of something. So it's typically you do picture analysis. And how do you take pictures? SEM, scanning electron microscope, is a good possibility. But that means it's a little slow because electron microscopy, you have to pump a vacuum and you have to have the machine available. Many times you have to register because so many people use one machine. Is there another possibility to do picture analysis? Yeah, the other electron microscopy, even more complicated. No. You want it quick. That's basically light microscopy. Yeah? And light microscopy is, of course, limited typically because it's a far-field optical experiment by the wavelengths that you use. But there are also different modes you can use. You can do dark field and bright field images. And in light microscopy, when you go to dark field images, you can see the fibers still because you see the scattering of these fibers. And that means if you do a bright field image and you can't really see much because the structure is so small, you only see some fuzzy things there. So you know already it must be small. And then you can go to the dark field image and you get indication that there are fibers then. You will see that it's not just a few spots or so on. And it doesn't tell you, of course, whether the fibers are now 300 nanometers, 200 or 100 nanometers, but you can easily verify you have fibers, and because of the physics effect they give you, they must be smaller than a micron for sure. And so you get at least the hint where they are. And many times that's a very good approach to quickly characterize these things. So you measure something, have a light microscope, put it there, and then you see immediately, oh, I'm below a micron already. Yeah? Okay, and of course, yeah, if you want to make it precise, you have to go to a SEM. So if you electrospin them, yeah, you get the fibers. This is as received as the earlier picture. Depending on the deposition conditions, you might have fusing of these fibers because you have wet polymer systems coming down, depositing on each other. And when you then when they're too wet, basically they can fuse and connect. But if you heat the system or use ethanol, evaporates usually quickly enough. If the distance is long enough between the fiber and the target, then you are successfully making single fibers. And when you heat treat them, of course, sometimes they break. Especially these materials break rather easily, the titania, because they're not single crystal fibers. They're polycrystalline. And here's a fiber. This is one of the thinner ones. And with a 20 nanometer bar, and this is, of course, TM picture now. And you see you get all this porosity in here. You have grains formed after heat treatment. And so these fibers cannot be too strong. But you see we can actually make really small structures. And this allows you to make similar compounds by that's the wrong direction, sorry. By using different precursors here. Yeah? So salt shale is available for a variety of compounds. Let's now look at another important thing with this system. So we talk about salt shale. Salt shale here is, of course, a reactive system. If you take this titanium butoxide and load it in your syringe, you typically work not in a glove box with controlled humidity, but you work in the lab environment. And even if it's just a short moment, you expose the whole system to air, and with air also water. And a small amount of water for titanium butoxide is enough to start precipitation. So the other thing we had earlier, where is it? Here, is this. So we want to make nanofibers. That means you have to get the flow rate really down. You're talking about now 0.3 milliliters per hour. And that means 0.3 milliliters, there's your solvent in there, a little bit of ceramic precursor, and some polymer. So if you really want to make large quantities of ceramic materials that are nano size, then you have to work for many, many hours, actually days typically. So this chemistry is not an issue. For example, for polymers, it's not so much an issue because you dissolve it, you have a solvent, no chemical reaction. But for this system here, you have a high reactivity, and if you expose this while loading the syringe, and then a few days later, while you electrospin, this precipitates, and you actually can't electrospin anymore. So what you need is actually a very specific system that can run for many days if you want to make nanofibers, large amounts of nanofibers, not just a few. And here's just the picture what happens. Titanium isobutoxide, titanium butoxide and butoxide in ethanol is, if you add water, immediate precipitation, of course. If you keep it open in air, just in 12 hours, it's precipitated. And so if you have it in a syringe, even it's sealed, because you transport it through air, you expect it to precipitate within maybe 3 or 4 days. And so we have to do something about this, and you can then do, of course, colloid science, chemistry, combined systems. And I'm just clicking through a little bit faster here. So what we do now is we make colloidal stable system, and we use a compound here. It's called 3-glycidoxypropyl trimethoxysilane. So this is nothing else but a molecule that, so you have basically here methoxy, CH3, CH3, and now here glycidoxypropyl. Maybe I have it on the slide somewhere. No, I didn't put it on the slide here. But you have here now a side chain that is longer, and of course it finishes with an epoxy, so oxygen here. Yeah? And this side chain does not react, so these groups all split off, and this chain does not react. So what happens here now is that you have colloidal stability. So when all these things react, you form little particles, SiO2 particles basically, because you have another precursor here, is TOS, that forms this, and then you have the surface decorated with these side chains. Yeah? Oh, triangles. And so you can all completely react these systems, and then at a certain point it stops, and that is pretty much defined by the amount of this compound that you put into the system, and then you end up with small particles floating around. And if these particles are small enough and still reactive enough, you can then turn them into fibers later on heat treatment. And yeah, so that's basically happening in the system here. Now you can also combine it with other compounds like titanium butoxide, and everything gets into a system that is then colloidally stable like this. And when you electrospin them, you come then here finally to systems here it's very difficult to see. These are then dense fibers of silica, and you find then on crystallization 1200 Celsius, you find then titania particles, for example, in it, but you can do it also with pure silica or combine it with some other compounds. So That's an interesting thing. Another thing that is possible, you can crystallize these compounds. If you work, for example, with alumina precursors, you can, and tin oxide, many others have been shown, you can turn them into single crystal fibers. This is then coming also from the heating profile and the dimensions of these objects. And yeah, when you do basically selected area diffraction, electron diffraction in the TEM of such structures, you find basically that we're capable of making single crystals. And another thing is, of course, you're not limited to just the shapes of a dense fiber. You can make also fibers that are highly porous. And then, of course, you can make them, because they're highly porous, the diameter total is then larger. You can make, of course, much larger volumes. And this is shown here. Within a few minutes, you can create, actually here, you coat an entire system of a hot plate underneath that way we're electrospinning on. So you coat this within a few short time frame. You see the flow rate is 25 milliliters per hour. So we're not limited to just the really slow flow rates. And here's the precursors for that. It's an alcohol, so it evaporates quickly. And and another solvent that doesn't evaporate so quickly. And what you can do by this then is the fibers are much larger, of course. You see it's in about the 20 microns thickness, but now you have porosity in the fibers, and because of the chemical reactions happening, it dries from the outside to the inside. You start to form a hollow inside in the system. And okay, so with this, we come to another area of applications that we may look into for reviewing papers, and that's many times reported for electrospun fibers, because you come to nano-size structures, and you can make this typical design here. So the fibers are basically lying on the surface and give you air pockets in between. And so you can move surfaces towards the Cassie state. Again, just here, so the Young's equation defines basically the vectors here and the contact angle connected to the vectors here for the contact angle of a liquid to the surface. Overall, it's connected to the surface energies, of course. And so it's a solid vapor interfacial energy, solid liquid, liquid vapor, and then equilibrium at the corner here at the triple point. And then where all three phases then connect. And if you roughen this, we had this yesterday's lecture already, then you have, of course, even higher contact angle, and that's connected through this here. So the actual divided by the projected area is basically put into this equation. So you get a higher contact angle, or cosine theta, but it responds in the contact angle. And then, of course, when you go to the Cassie state, now we have then, of course, the fraction of surface area contact liquid and fraction of areas with pockets in touch. So this is just an example for the electrospinning of materials that also now are porous or coaxial. This one is a coaxial filled system that we're going to spin now. So there's a whole bunch of varieties. So you have the core solution, sheath solution. And the interesting thing is now with the electrospinning here, you only need one solvent that responds to electric fields. Both systems don't have to respond to electric fields. And then a cone forms, and the structure that you have here typically stays as long as these two liquids are not miscible. When they're miscible, then you end up with a random structure, which might be also of interest, but it doesn't have to be interesting. And if you want to make it really separate, then solvents should not mix. And it doesn't matter whether the inside or the outside responds to the electric field. Electrospinning will happen if one of them does. And so you can make such structures here. Else the setup is pretty similar. Now you have to, of course, control the pumping of two liquids, and you have to figure out the flow rates for the dimensions that you want to achieve in your core sheath systems. And as I mentioned, when you make such structures, here, this is now PAN, polyacrylonitrile core, and Teflon AF. It's a modified Teflon that can crystallize on the surface. And we make such fibers as shown here in the TEM. Then you get typically not just the Teflon behavior, basically very low contact angles. You get a basically super hydrophobic state by repelling this through the Cassie-Baxter state. Yeah? So you can get to contact angles of 150 degrees for water, which is super hydrophobic. And let's see, is there anything else I had here? This would be more about characterization. I think we can stop here, actually. Let's see, is there anything else? Yeah. Maybe in the end of this lecture today, I want to just focus on a few other things for being creative. So you've seen we have a lot of phenomena in nature where electric fields occur. We have basic clouds are being charged up, tribord charging of water against air, and then you start to have clouds, typically positive charges. That means you have lightning phenomena and so on. So for years people have observed this, but where else are strong electric fields that might actually do something like electrospinning? And also nature electrosprays in thunderstorms, yeah, so that's happening because you have strong electric fields. So where else do we have strong electric fields outside? Besides storms?
Some fish.
Huh?
Some fish.
Fish, yeah, but they're in water, so yeah. But yes, they exist. There are some eels, but no, I mean man-made strong electric fields. Hmm? Yeah, it's called power lines. Yeah, so several 100,000 volts landlines that going through. So when water drops on them, they also everything around is a lower potential, so they also start to electrospray. And if you have polymers in there, they electrospin actually into the atmosphere. Yeah? So that's something. These are things where you have to, when you're critical thinking, you learn something and you apply it to others, and it's like, oh, this must be happening here too. And there was one thing where people were also really shocked with such a phenomenon. If you want to purify the air, you use, for example, electrostatic precipitators, because a lot of the compounds that are floating around in air are actually electrically charged. If they're not, you can actually use a corona charging process to make them charged. But if they're not, if they're already charged, you just basically use two metal plates and let air stream through, and then because of the charge of the particle, they will deposit on the collector. So that's a typical way of collecting oil droplets if you work in a factory where they have a lot of oil being evaporated. Oil, of course, when it's in the air, the same like water, when it's cold enough, it forms fog. Oil after evaporation also forms small oil droplets that float in the air in the area where you work and where you breathe. So they want to get rid of these droplets, and of course they put in electrostatic precipitators, for example. So electrostatic precipitators also work with strong electric fields because you want to trap all these particles, and that means the oil is slowly pulled through from a fan or from other electric fields that you can do to pull them in. And then when it hits the precipitator, it deposits as it should do. But we already learned now what happens with liquids and electric fields. You collect all the droplets, which are macro size, basically, that are floating around. And once they deposit, they form a thin film of oil. And now it's a liquid in electric field, and you start to form a cone again, and you start to electrospray. So on the one side, you get the large particles in, deposit them, and then the system starts to electrospray small particles and they can escape the system again because they're more towards the end of the system where you electrospray. And so you change actually with an electrostatic precipitator the air in the factory from micron-sized droplets to nano-sized droplets of oil. You're not removing the oil. Yeah? So these are things that are surprising, but with enough critical thinking, with understanding, then you can analyze these systems. What else can you do? Electric fields. You can, we talked about this in the beginning here. So you deposit your charged fibers or your charged particles when you electrospray just onto pretty much anything that has a lower potential. So if you're outside, let's say in a field, and you have crops that have insects on them, and you want to hit these insects with a pesticide, for example. Typically right now you just spray and hope you hit something. But the possibility is now that you take your pesticide and charge it with a high potential. So you form small droplets. First of all, they're much smaller. You have to, of course, take precautions that it's not dangerous to anyone else that is around. But then these droplets will deposit anywhere with a lower potential. And the beauty is now that the lower potential is all around the plant. So it will, of course, deposit also on the soil, but it will deposit not just on the top of the leaf, it will also deposit on the bottom of the leaf and anywhere in hidden areas of the leaf. Yeah? So you can certainly coat plants with an electrospraying unit and apply this basically in the field. So this has already been demonstrated. You can hook up such devices to a tractor, and you don't have to use pesticides, but you can put fertilizers or other things in small concentrations defined on the units where you want them. Possibility to harvest chemical compounds from a plant that are in solution without cutting down the plant. So you basically just have to turn on the voltage from time to time, have collectors around with lower that are grounded, and then you can collect everything. Yeah? So that's a pretty interesting concept to collect drugs. And one of them is, of course, a taxil that is from a specific tree. And right now you have to cut down the tree after it's about 50 years old to harvest the chemical. It's a powerful cancer drug. And so you have to grow another tree for 50 years instead of just harvesting what's in the tree and then reusing it the next year again. Yeah. Okay, so these were some thoughts about this. And I said next week we're student presentations. After that, then we do the critical analysis of literature. And then we have the final exam. And then the semester is over already. Huh? Yeah. Okay. Yeah, thank you very much. That's all for today. And class dismissed then.